Okay, so it's 3 o'clock. So I took the midterm review, because of that we skipped one discussion. So today we are going to cover 3 topics. They are not. So remember that dynamic stability and equations of motion has been covered up until now. Then you have Euler angles, and then you have linearization. So these 3 things are going to basically form the toolbox of the remainder of the course. I am not going to take up stability derivatives today. I know that there is a small homework problem in problem 2, but it's not that difficult. If you face issues, I'll take it up on Monday's office hours. So let's talk about dynamic instability. So up until now, we were doing static instability. Static instability was what? The inherent ability of the aircraft to return back from a disturbance. But now we want to see, so is Cm alpha less than 0 sufficient for an aircraft? The question is this. So if you recall from your lecture, it is not. Why? Because if we do a simple experiment where we mount an aircraft about its pitch axis, switch on the wind tunnel, then because of the pitching moment, the aircraft will pitch up. But if I deflect the elevators, then I can bring the aircraft back into position, and the equation that we get is theta double dot is equals to m theta, right, or k theta, you can say, not m theta, k theta minus k theta. So it behaves as a mass spring system, which means that your aircraft is going to keep doing this thing, which is not desired. So we want some kind of damping. So how are we going to introduce damping? We will see that when we write down the complete equations of motion. So remember that the equations of motion were nothing but F equals ma and I m. So I should write this small m, F equals ma and capital M equals I alpha. So this gives you 6 degrees of freedom. Anybody who does not understand degrees of freedom? So degrees of freedom is basically how much information do you require to describe a body's motion. So if you had an arc like this, and let's say I had a ring which was onto the arc, then the ring can only slide this way and this way on the arc. So if you were given the equation for the arc, right, you can find out x, that would give you the like if you chose x, that would exactly give you the location of the ring on the y axis, right. It's not like x and y are independent. If you know x, you can find y. If you know y, you can find x. So there is only one piece of independent information. So that is why we say it's 1 degree of freedom. What if we had a 2D plane? So if you read some textbooks, higher level textbooks or papers, they tend to use something called R square. So this, the single line is called the real number line. So this is the symbols for real number, and then like real numbers in one direction, real numbers in another direction, you get a plane. Now if I had a point mass on this plane, it could move this way independently and it could move this way independently. And if it moved any other way, then you can express it as motions about this and this. So this is a 2 degree of freedom system. Similarly, if I had a cube and I had a point inside of it, then it could move in 3 independent directions. This would be a 3 degree of freedom system. So this is for a particle. Okay. Now what happens when you look at me? I am not a particle, I have certain features on my rigid body, and I can align something called, or I can define something called attitude, not the one we are usually concerned about, but relating to angles. Okay. So, attitude is the angular orientation of a body about its own axes. So, I can say that if I define one of my axes to come out of the nose, then I can say that I have turned this way, or I have turned this way, or I am simply turning around this way, which means that in addition to translational degrees of freedom, which are all there for a particle, we also have rotational degrees of freedom. So, that is why any rigid body will have 6 degrees of freedom in general. Okay? And that is why for each degree of freedom, how it is evolving with time, we have to write down the force equations and moment equations, which will give us 6 equations of dynamics, and we have to solve those 6 equations of dynamics to understand how does the rigid body move in space and time, and how also how it is oriented. Not just movement, but this is like the dynamics of movement and orientation. Now, what was the next problem that we faced here? The next problem we faced here was that everything is written with the frame of the aircraft, right. You are writing, I mean we draw an aircraft like this, and we say that this is U, this is W, this is V, right. If you roll about U, this is like angular velocity P, oh this is V. If you roll about this, this is Q, and if you roll about this, you have so this is yaw rate R. So, you are defining all these things, but where are these like what is the reference frame for this? Like you understand, to define any vector, first of all what is the first thing that you need to put down on a sheet of. So, let us say I had a, forget about all this, let us say I have a blank board and I want to draw a vector 1, 2. What is the first thing that I need to do? If I tell you this is a blank board, come and draw the vector 1, 2. Yep.
You like a reference point?
Yes, first you need a reference point. What is that reference point called? Origin. And then what is the next set you need?
Slope,
axis. So, we will go ahead and declare this as x. Is one axis enough to traverse the entire whiteboard? So, we will need another one which is independent of x. And now, I can say that okay, 1 means move 1 along x, move 2 along y, and this is my vector, right. So, to define any vectorial quantity, you need a origin and frame or axes. And what is the origin here? The origin here is the CG, and about the CG we define x body, y body and z body. But the problem is, okay, my aircraft is flying in the air, but we live on earth, we have to live on ground, we have to conduct our normal operations on ground, we have to control aircrafts from ground. So, we need to know the forces, velocities, angular velocities, blah blah of the aircraft with respect to ground. How is that going to happen? Because this aircraft could be flying in any attitude, any orientation with respect to air, and it will see air moving relative to it in that direction. But we here down on earth won't be seeing any air moving. So, we will have to convert these velocities and angular velocities into our frame. So, if you recall from MAEAT, if there are two particles, let us say this particle is moving at velocity v1 and this particle is moving at velocity v2, right. And if this is the observer and this is the target, then what do we say? The velocity of the target with respect to the observer is going to be v1 minus v2, right. But this is just for velocity. What if you had rotation as well? Things get complicated. So, why things get complicated? Because if let us say there was a vector A and it was rotating. So, it's rotating about this direction, it rotated by a very small amount d theta. So, now this is vector A at some time instant t 2, this is at some time instant t 1, right. Now, the magnitude of A has not changed. What has changed? The direction, right. So, how do I quantify that what is A at time t 2 minus A at time t 1? Because I know that dA by dt is like, if I look from my frame, I am drawing it on the board, it is 0, sorry not 0, yeah not 0. But if you were someone who is like sitting on the vector and you had no, like completely forget that you have 5 senses blah blah, you are a machine which has been given sensors, there is, and you can see the magnitude of the vector or feel the force or the velocity, the magnitude has not changed, the direction has. So, how do you quantify that change? The change is simply, so we want this vector minus this vector, which is going to be this vector, right. And this vector is almost perpendicular to A. It is actually, if you keep on reducing d theta, this vector will become perpendicular to A in the limit that d theta goes to 0. Okay. What else? Can I measure the magnitude of this thing? So, let us say this is the magnitude of A, this is the magnitude of A, it is going to be the same, and I can split this is d theta by 2. So, half of it is going to be mod A sin d theta by 2, which means the total change in magnitude is going to be. So, I have been able to find out that this is going to be 2 mod A sin. So, sin d theta by 2. Are we done? Are we done? This is what? The left side of the equation is what? A vector. Is this a vector yet? So, this is the scalar part, we have only found out the magnitude. So, we know that if d theta is like going to be extremely small, the change in direction is going to be exactly perpendicular to A. And how do we express that? If you look at, so it rotated like this, so this was omega, right, and you cross omega with A, you get the direction of change. Do you get what I am saying? This was omega, this is omega cross A. So, if A is rotating, then you have something called omega cross A divided by modulus of omega cross A. Why did I divide by modulus? Because omega, I mean you need to take the unit vector in that direction. We have already decided the magnitude. So, we need the unit vector in that direction. And to define, I mean you can't just go on defining let us B be the perpendicular blah blah and so on. You have to define this vector in terms of the vector that you have. So, you know the angular velocity, you know the vector, and you take the cross product of the angular velocity with the vector, you get the direction, but then you need to normalize it, because the magnitude of your vector and angular velocity necessarily need not be 1. So, that is why you have this relation where, okay. So, now if I were on the frame that was attached to A. So, let us say I attach a frame to A and the frame also rotates like this. Would I see any change in A? I wouldn't, because I am also moving with A. I don't see any change in direction. It's like I am attached to this marker. Forget that you have rooms and blah blah. It's okay. You have eyes, you only have eyes. You are in a white room, absolutely white room. You have no idea where is forward, backward, right, left. Okay? You are absolutely freely floating in space. The only piece of information you have is that there is a marker pointing right in front of you. Now, the marker is moving with velocity omega, right, and your nose is aligned with the marker. Now, someone else is observing you from outside, let us say God, and he is seeing that you are doing this. In his reference frame, you are moving with some angular velocity, but the only thing that tells you that something is moving is the marker in your world. If the marker is like your eyes are aligned with the marker, you do not see any change. The marker is still like the way it was in front of you, but you have no idea that you are moving along. And also, like, this is kind of a metaphysical idea, but we as humans have a nervous system which is not very good at detecting constant velocity, but is very good at detecting acceleration. You can feel an accelerating car, a decelerating car, but you can fall fast, like you can fall asleep very fast if the car is running at a constant speed on a freeway, right, because your body does not notice the change between a car running at 40 miles per hour or at 80 miles per hour, but your body will feel the difference of going from 40 to 80 miles per hour. So, you can observe acceleration, but if you are moving at constant velocity, angular velocity or translational velocity, and your body frame is also moving, from the inertial frame your vector is not going to be the same. So, we take the derivative of the vector in the body frame and then we need to add for rotation. So, this is the extra part that you see in the inertial frame. So, this is your truth, this is the total truth. Okay? And when you go ahead and plug these things into these things here, you get the 6 equations of motion which are very scary looking and should always be on your cheat sheet when you are on your final exam. You do not need to memorize them, but why we can't simply write like for example, why we can't simply write equations of motion in this frame. Now, do you get it? I mean, you could have written equations of motion in this frame, but then this is a non-inertial frame. So, you would have to account for apparent forces, apparent moments, right. So, what would that, what problem would that create? That would create a lot of mess about like your frames changing at each moment. So, now you will have to keep updating your forces as well. But if you just know the movement of the frame and you have written the forces and moments based on this equation, right, then you can translate all the information in terms of change of coordinates. So, if you feed in like, okay, my coordinates are changing this way, my frames changing this way, so my forces, velocities, angular velocities and moments will change that way. But if you are doing everything in this frame, then you do not know how the frame is moving and you have to account for apparent forces, apparent moments and so on and so forth. Okay?
Why do you get like 2 magnitude of A and the sine of that?
It's triangles. So, if you have a triangle like this, I drop a perpendicular, this is side 2, let us say this is side 2, this is some angle theta. So, this is going to be theta by 2, this is going to be theta by 2. And now, this is 90 degree, this is the hypotenuse. So, this is going to be 2 sine theta by 2. So, what is the total going to be? 2 sine theta by 2 plus 2 sine theta by 2, that is 2 times 2 sine theta by 2.
2 times 2, okay.
Actually, I did a horrible pedagogical mistake, I do not know why. Let us say this is A and this is A. So, this is going to be A sine theta by 2.
Okay.
And what is the total length?
Twice of that. Right?
Twice of that. So, that is why you have 2 times mod of A, which is the magnitude of this sine d theta by 2. Okay? Excellent. And one more step that I would like to show you here is, so recall that how do you take derivatives? You take derivatives by saying that this is delta t limit delta t goes to 0, right. I would love to talk about limits for an hour, but this is a dynamics class. So, limit is just like, it is like vanishingly small, but not exactly 0. You are like just stopping before 0. I even should not be saying. Same thing here, limit delta t tends to 0 divided by delta t. Now, as delta t tends to 0, what is going to happen to d theta? It is also going to like be extremely small, which means that we are at liberty to use the small angle approximation. So, I can write this as limit delta t tends to 0 to mod a d theta by 2 divided by delta t times omega cross a, and this is mod omega mod a times sin theta. Theta is the angle between omega and a. In this very special case, omega and a are perpendicular, so sin theta will come out to be 1. I should actually just call it sin beta. Okay. So, now what happens? You go ahead and cancel this, and the only thing that matters is d theta by delta t, which is change in angle divided by change in time, which is what? The magnitude of angular velocity. So, you get magnitude of angular velocity, magnitude of a times omega cross a divided by this thing. So, if sin beta is 1, that means the angle between your vector and angular velocity is 90, then it is 1. So, you will see that omega a will cancel out, and the only thing that remains is omega cross a. So, this is the extra truth coming from the inertial frame of reference, right. Now, be cautious. I mean, in this course you won't need it, but future in life, if your vector is not aligned or not exactly perpendicular to your omega, like for example, if I had this coffee mug, right, then the angular velocity is like perfectly aligned, fine. What if it was like this? This was the principal body axis of the coffee mug, and this is the omega. So, the cup is going to move something like this, right. So, it won't exactly be sin beta equals 1, you will have to account for that as well. So, that is why we need to learn how to take the derivatives of vectors which are easier to express in the body frame. Why? Because as an aircraft, it is easier to measure air velocity. Obviously, you have to measure air velocity on the aircraft, you have to measure your acceleration and Euler angles based on your IME unit. So, everything your lab and equipment are in the air, but you are controlling it, navigating it, managing all the aircrafts from earth. So, you need to translate the forces, velocities and everything into earth's frame, and that is why we write the 6 degrees of freedom using this principle. Okay. So, there is nothing. So, this is like, so the first part, dynamic stability and equations of motion, is more like the ingredients of the food that we are going to cook for the rest of the quarter, right. Then we have Euler angles. So, Euler angles is not, so dynamic stability and equations of motion you can think of as the veggies and meat. Euler angles is basically like the next step that helps us move from one orientation to next. So, what is Euler angle? So, for Euler angles the concept is very simple. Euler came up and proved that if you had a body, a rigid body, right, and you wanted to move from one attitude to another, that means if I wanted to go from like this to final orientation something like this, I need at most 3 movements or 3 rotations about 3 different axes at most. Okay. So, at most why? Because if I am here and my attitude is finally like this, then it's just one rotation. But what if like I do not want to be the subject, we will do something right now. So, and why is that required? Let us see. So, you are, let us say that you are an air traffic controller, okay, and I am the pilot. So, my So, we are right now here you are on at the ATC, excellent, this is the runway and this is the flight here. So, this is the inertial frame of reference, this is the body frame of reference. Right now the body frame is completely aligned with the inertial frame because everything is on the ground, perfect. It starts to roll up, the aircraft is taking up. So, what is the first thing that aircraft does? Pitches up. So, which means that like my body frame, or let us say that if I had to go from this body frame to this frame, B1 frame, then I would have to rotate about what? About the y by some angle. So, if I want to go from body frame, actually here inertial frame, if you take some rotation positive phi about y, then you will end up in B1 frame. Okay. Now, I am in nose up and I am still traveling, I have not changed my attitude. Okay. Translational Euler angles has nothing to do with translational part of the motion, only rotational part of the motion, right. So, now I am in B1, I am taking off. Now, I have been told that another aircraft is landing, so change your heading a little bit. So, I am asked to roll, right. My roll is going to take me in a different attitude. I am not moving forward, why I will tell you, because roll also induces some yaw. Okay. So, when you roll your aircraft, you are also going to turn like this, like if some of you play Microsoft Flight Simulator, then this is a very difficult thing to control on military aircrafts. You should play that game, it is better than COD. So, now if I were to roll like this, what is the axis I am rolling about? X axis. Okay. So, I roll by some positive theta about my x axis, I reach the B2 frame and then I have yawed. So, if I do not know if yawed is the correct word, but I am yawing about z with some positive psi to finally reach this configuration here. Now, my aircraft is here like this. Now, because my aircraft is here, so now this is u, right. This is u, this is v, this is dub, this is p, this is q and this is r. And if I trace back to the inertial frame, it has nothing to do with u, v, dub here, completely different frame. So, how do I find out? So, now my aircraft is saying that I am flying at 400 knots airspeed, because they only know airspeed, they can't have cameras and 1000 sensors to look at to reference. One way is obviously you have multiple cameras, multiple sensors under the belly of your aircraft or over all your aircraft, through which it is geographically mapping the earth below, which would be extremely compute intensive and too much information to process. So, we depend on gyroscopes and pitot tubes. So, pitot tubes are going to give you the velocity and gyroscopes are going to tell you that how much Euler angle have you changed from the start. Okay. So, now the pilot reports to me that our velocity in the body frame is going to be some u v dub and our angular velocity right now is some p q r. Now, how do I know with respect to ground what is my? So, when you sit in an aircraft, it will show you ground speed, air speed are two different things, right. Have you ever tried that screen? I do not know, Southwest does not have that, unfortunately. So, now I want it to come back to, now I want to process the information in inertial frame. How can I do that? I have to come back step by step, right. And to do that, we use something called rotation matrices. So, before we do this entire exercise, let us look at a simpler example as to how we build rotational matrices and how we remember them. You actually do not need to put them on your cheat sheet and waste space if you understand how rotation matrices come into the picture. So, let us take a 2D world. This is x1, this is y1 and obviously, this is z1 and then I rotate this to get x2, y2 about z1. So, where is my z2 going to be? Okay. So, the axis about which you are rotating never changes, first principle. That is why you will see always axis, angle, sine. Okay. Why sine? Because if you point your thumb in the direction of z, if you are going this way it is positive rotation, if you are going the other way it is negative rotation. Excellent. So, now let us say I had a point A comma B, which was written when I was in x1 and y1 frame. Let us say it was like 1.0 and 1.75, I do not care. Now, if my world has rotated a little bit, is it still going to be 1.0 and 1.75? No, it is not. So, how do I find that out? It is very simple. So, you go ahead and if you go ahead and derive this, which is not the objective of this discussion, found in multiple books as well, you can write down the coordinates in the new frame as cos psi, sin psi, minus sin psi, cos psi times x1, x2. You have to multiply this matrix with the older coordinates, which rotates the coordinates into the new frame. What if I had a 3-dimensional world? I would still be rotating about z and my z coordinate would still won't change, right. If I had a point somewhere here in outer space. So, the z axis is still this way itself. So, its z component is still going to be the same, which means that if I had a z2 here, y2, y1 sorry, z1 here. So, z2 is going to be exactly equal to z1, nothing else. So, I know that there has to be a 1 here and x2 and y2 have nothing to do with z. So, there would be zeros here. So, in a rotation matrix, if you are rotating about z with positive psi, then you go and look at the third like 1, 2, 3 on the diagonal 1, 0, 0, cos psi, sin psi, minus sin psi, sin psi. Oh sorry, horrible mistake. Cos like this, sin like this and negative here. Similarly, if you rotate about x by theta, you would have, what is x? X is the first coordinate, first axis. So, which diagonal should I, where should I put the 1? Okay. There is just one problem and I like to call it the y devil. First step is as it is. What place do you want me to put the 1? And its rows and columns are going to be 0. Okay. Now, we are rotating by phi. So, this is going to be cos phi, sin phi, cos phi. Why the devil? Because here the minus sign is here. So, in z and x, remember that the minus sign is in southwest, but in y the minus sign is in northeast. And to be honest, it is a very simple, like position of the diagonal fixes everything, cos theta, cos, sin, cos, and then where to put the minus sign. 3 steps, 3 mnemonics, you do not need to put rotation matrices on your cheat sheet if you practice enough, because you will require a lot of other things to be put on the cheat sheet. We still have 4 more weeks to go. So, everyone is here with me up until here? Okay, I need to speed up. So, how do we, so any homework problem, anything is going to be the same template, okay? There is no heavy concept here. It's once you understand, like there is no like a lot of variety or something like we can trick you with. It's the same template if you understand the concept. So, now my target is that I have, just for real life examples, I have the velocities and angular velocities of the aircraft which are being measured on the aircraft. So, they are with respect to aircraft's frame, but the control and navigation has to be managed by the air traffic controller who is on the ground. So, he needs to know the velocity or she needs to know the velocity and other stuff from the ground frame, which means I need to take this information back to the ground frame, right. Which means that if I go from B to B2, then I would rotate about z, but minus psi. So, two things are very important in Euler angle questions: setting up this picture, that how am I moving from frame to frame, and second is direction of information. If I had given you information in inertial frame, so now if you give some commands computing from the inertial frame that change your velocity by 10 meters per second. So, this information now has to travel in the other direction. So, it will go through the opposite order of rotation matrices, but now I am sending the information back. So, this will be rotation about z with minus psi, this will be rotation about x with minus theta, this will be rotation about y with minus phi. So, now you have, so your total velocity of the aircraft in the inertial frame is going to be r y minus phi, r x minus theta, r z minus psi times velocity in the body frame. What if it were the other way around? Like I was doing a wind tunnel experiment, right, and I knew that like let us say that I have a quadcopter which I am controlling inside of a wind tunnel. So, now I know that the wind tunnel is running at a velocity of u infinity. How do I, but the quad flapper or quadcopter could be like this, could be like this, could be moving around, it is just blowing air, and the quadcopter or flapper is trying to be stable in that free stream, right. So, how do I convey this information if I know the attitude of the frame? So, I can measure I can put visual markers on the flapping wing flapper or the quadcopter. I can put it in front of a motion capture camera and I can measure its Euler angles, which means that if I can measure its Euler angles, now the thing is that why am I so bothered to look at the velocity in the body frame? Because the quad flapper or quadcopter will not see u infinity as the only velocity, it will see different components of velocity, which means that it will start seeing forces. Why? Because aerodynamic forces are squared of the velocity that the body sees. So, it will start seeing forces which are in 3 directions, it will start seeing moments which are in 3 directions, even though your wind tunnel is running the velocity only in one direction. Okay? So, it is very important that we have a mechanism to transfer information from one frame to another. Sometimes we want to read information from the system, sometimes we want to send information to the system. So, communication with the system, anything, be it car, be it satellites, be it flights, this concept is universal to the dynamics of remotely controlled vehicles or remotely navigating vehicles. Okay? Any concept with any problem like how to figure out Euler angles, and also like for any two kinds of rotation there will always be 12 options. Like if this was the initial configuration and this was the final configuration, then see like I can make up a lot of options, like I go like this, go like this, go like this. This is one way. Okay, let us start again. This is another way. Okay, then this. Okay, then like this. 3 steps maximum you will reach from one attitude to another, and you can do it in 12 different ways always. You just need to keep choosing the axis randomly. Why? How does this 12, all of you have taken probability and counting at some point in life? No? Okay, you understand this simple concept that let us say I wanted to go and have ice cream. Okay? I have ice cream every night, and now there is the question that whether I want my ice cream in a cup or in a waffle cone, and then there is the option of either taking chocolates or almonds or pistachio. Okay, 3 flavors, two things. So, how many total ways of, like, how can I have different, like, how many total ways of having ice cream?
The product of them.
Should I use boba as an example? Then you will get it
Like 2 times 3.
2 times 3, right? 6. So, what do? You go ahead and create a blank for cup or waffle, and then you say, okay, the other blank is for flavor. I have 2 options here, I have 3 options here, I get 6. Okay. Now, what are we doing with these rotations and movements? The first thing we need to choose is the axis about which we are going to rotate, right, and the angle and so on and so forth. So, Euler says 3 steps of rotation. Okay, 3 steps. I have how many choices for the first step? I can choose either x, y or z. Fine, I have 3 choices. Good. Now, let us say I chose x and rotated the frame. Does it make any sense to choose x again? Because you can combine both the rotations together. So, now you are out of one option, you only have 2 more options left. You have to either choose y or z. Now, same again, let us say I choose y. So, now you have x and z as options, right. So, you can choose 2. Hence, the total number of options for any 2 orientations is going to be 12. Okay. So, to move from one orientation to another, you always have 12 ways of doing it. So, if you can't like figure out something, there is always like there are 12 ways you can do the problem. Okay. Do not worry about it. Lastly, I have 10 minutes and that. So, dynamic stability and equations of motion, the main concept is that static stability is not enough for time varying purposes, for long term behavior. We need damping, that is what dynamic stability's core message is. Equations of motion tells you that we need to convert the information being gathered on our equipment into the ground frame, and we should always write our equations of motion from an inertial frame of reference. It is much easier to study them, otherwise we will have to keep accounting for apparent forces, apparent moments all the time. Then we came across Euler angles. Euler angles help us transfer information from one frame to another. Some information cannot be accessible in the inertial frame. I mean, how do you know what air velocity is the aircraft seeing at 33,000 feet from ATC? Either you are going to keep sending a following aircraft which is always maintaining inertial frame, or it is just better to convert it back into inertial frame values. The next thing is linearization. So, what is linearization? So, as we all know that these set of equations are extremely complex, right, and they have multiples of like r times v, u times like velocity times some angular velocity. So, these equations are not linear in velocities and what do you say, like they are non-linear equations. So, it is much more difficult to study non-linear dynamics. So, what do we say that okay, we will, so let us say that the dynamics of some system looks like this, or the trajectory looks like this. I can't study the entire trajectory at once, but I will say that okay, actually I should make a more relevant. So, this is something called the mission profile. This is how realistically the mission profile of a general aviation passenger aircraft looks like. You have takeoff, climb, cruise, and then flaring and landing down, okay, in multiple stages. That is why you feel the aircraft like as if free, like you will, if you notice closely, then the larger the aircraft, your pilot will try to put it into free fall for a second or so when you are landing. It is much more easier to gain flare using that maneuver. So, we say that okay, here you know it's non-linear and I can't like make a model for the entire thing. So, I will go and study each phase, I will go and study each single maneuver, and that is why we are going to linearize. Linearize as in what happens in cruise. My u is going to be non-zero and I am going to be flying at some theta naught which will be same as alpha naught, and this would be non-zero, right, stable cruise condition. V naught, dub naught, q naught, r naught, p naught, all of these are 0, no side slip, no up down motion and no rolling, yawing or pitching. I am flying at fixed angle of attack forward with a constant velocity. Now, I ask the question that okay, if there is a small disturbance, right, do I need to like solve for the entire nonlinear physics, or actually like it becomes simpler to solve the problem? Let us see. So, let us go and study that what happens in the x force equation. Okay. So, the x force equation come on. Yeah, so the x force equation is given as m u dot plus q dub minus r v plus q dub minus r v equals x minus m g sin theta. Now, if you give me this equation and say that okay, now tell me what is going to happen to a little bit of disturbance while you are in cruise, I will be like this is very difficult to analyze. So, let us see. First of all, whenever you are asked to linearize, you will always be asked to linearize about a point of maneuver. It makes no sense to just tell someone that linearize this equation of motion. You have to linearize about a point of operation. So, the point of operation here is cruise, and that point of operation will contain like it will be kind of like constant force, constant moment, something like that, and you will have certain parameters associated with it. Okay. So, what happens at cruise? You need to first go and study the trim or equilibrium equation. So, what does the equilibrium equation say? U dot is 0 because my aircraft is moving at constant forward velocity. Q, dub, R, V, all of them are 0. Force is not 0 and obviously gravity is there. So, but I know that x minus mg sin theta is going to be 0, this much I know. Okay, fine, which means this entire thing on the right hand side at equilibrium is 0. You are asking me the question what happens if I get disturbed from equilibrium? Fine, I will go ahead and write out the perturbations. This is the second step in linearization. You simply go and say that u is equals to u naught at what I was at equilibrium plus some change in u. Okay. Same thing q, q naught plus delta q, w, w naught plus delta dub, so on so forth, and then I will go and feed it into the equation, and then I will see that okay, let us study how the disturbances or the perturbations behave with time. So, can I use u directly in the equation? I can't, I have to take the derivative with respect to time first. So, I have u dot equals u naught dot plus delta u dot, but what was u naught? A constant. What is the derivative of a constant with respect to time? 0. So, which means that u dot will be replaced by delta u dot. So, go ahead and write down m delta u dot. Then q is q naught plus delta q, where q naught is 0. So, q is only delta q. W, if I want to linearize, w naught plus delta w. So, in cruise flight w naught there is no equilibrium velocity, but there might be small disturbances. So, delta w only. Something not clear?
Is q omega and
Yeah, q are the angle, p, q r are the angular velocities.
Are they come from like chain rule or like what? Why we multiply q omega and the x v or something like that?
This you are saying?
Yeah, the left hand side, the q.
Oh, this is from the equations of motion. You need to go and review the equations of motion. Yeah, this comes from this vector that I was, this comes from this thing that I was trying to explain, that if you take the derivative of a vector in the inertial frame, you will get derivative of the vector in the body frame plus the omega of the body frame times a in the body frame. Okay. So, now you go ahead and feed in your perturbed variables. So, you will get delta q times delta dub minus delta r. Actually, I can write it completely just for so that you understand. Q naught plus delta q times dub naught plus delta dub minus r naught plus delta r v naught plus delta v equals x minus mg sin theta naught plus delta theta. So, now since this is cruise, q will be 0, q naught will be 0, w naught will be 0, r naught will be 0, v naught will be 0, right. What if this were a turning up maneuver or a pull up maneuver? In pull up maneuver, your v, so see what's happening in pull up, okay. Your w is still 0, with respect to your body you are not moving, with respect to your body you are only going forward. So, u naught is the only thing that is non-zero, v naught and w naught are 0, but what are you doing? You are pitching up, which means your q naught will be non-zero, and you might be pitching up at 0 angle of attack or non-zero angle of attack, does not matter. Okay. So, in different conditions, in a pull up maneuver, in a climb maneuver, in a cruise maneuver, in a flaring and landing maneuver, you would have different combinations of zeros and non-zero variables, right. Now, if I go ahead and simplify this, I get m times delta u dot plus delta q delta dub minus delta r delta v, which is equals x minus mg, and if I go ahead and expand this will be sin theta naught cos delta theta minus mg sin delta theta cos theta naught. Now, delta theta is a very small angle, right. We are using small perturbations. So, I can approximate this as 1 and I can approximate this as delta theta. Now, look what happens when I approximate it as 1. What do I get? X minus mg sin theta naught. What did I have at equilibrium?
0.
Which means that a part of your equation must cancel out after you write down the perturbations, which that information will come from equilibrium. Okay. So, this is 0. So, what is left is m delta u dot plus delta q delta dub minus delta r delta v equals minus mg delta theta times cos theta naught. Now, g is a constant, m is a constant, delta theta is some finite small value and cos theta naught is also some fixed value. And we know that delta theta is very small, like g is 10, mass is obviously in thousands and it will get cancelled out ultimately. Cos theta naught is somewhere between 0 to 1, okay. And because obviously the angle of attack is small, cos theta naught will be closer to 1. Delta theta is like very small, 10 to the power minus 5, 10 to the power minus 6, because we are looking at very small disturbances. Now, look at these terms. These terms are two small terms multiplied with each other. This is one small term multiplied with other big terms. So, I can say that this term will definitely be much smaller than this term and that term. So, I can say that since there are two higher order terms, I can neglect them, and finally, my linearized equation is simply going to be delta u dot is equals to minus g delta theta cos theta naught. So, now if someone comes and asks me that what are the perturbation dynamics about cruise condition, then I can tell them that if I was flying at a positive angle of attack and you like basically what will happen is if I have a disturbance, delta u dot would be negative. That means if I got a positive disturbance, the airplane would try to slow down, and if I had a slowdown, the airplane would try to catch up. Okay. So, I could make this comment only after linearizing about small perturbations. So, remember that I used small perturbation in this analysis, that is the core of this thing. And then in the next discussion session, we will discuss more about stability derivatives. That is all for today.